Chemistry 3331, Physical Chemistry 1. This section is about the perfect gas or ideal gas. You have learned ideal gas laws in general chemistry. Since we are going to use them in the later chapters, it's a good idea we go over these materials in chapter 1. As we know, matter exists as different states: solid, liquid, and gas. A solid maintains a fixed volume and shape. A liquid maintains a fixed volume but adapts to the shape of its container. So liquid has a fixed volume but can change shape. A gas expands to occupy whatever volume is available. In other words, a gas can change both volume and shape. So what makes this difference? Let's look at these states at the microscopic level. At the microscopic level, in solid states, molecules or atoms have strong intermolecular interaction. This strong intermolecular interaction lock the atoms or molecules in certain positions, so solid cannot change volume and shape. In liquid, the atoms or molecules have moderate intermolecular interaction, and therefore the volume cannot change. But the molecules or atoms can move relative to each other, and therefore the shape can change. In gas phase, molecules are far away from each other, and so the interaction is weak. And therefore, the atoms or molecules can move or occupy whatever volume is available. The difference of intermolecular interaction is responsible for the different states. It is important to remember that in the gas phase, the intermolecular interaction is very weak. In fact, when the intermolecular interaction is zero, when there's no intermolecular interaction, we get an ideal gas or perfect gas. In the next section, we're going to show that when we assume molecules are dots moving randomly in all directions, there's no intermolecular interaction, then we can use a statistic to derive ideal gas law. Gas molecules have unique properties compared to solid and liquid. For example, a gas expands to fill all available space. Gases generally have low density, less viscosity, and exert pressure on the walls of their containers. Gases have the ability to diffuse into each other. And remember, in gas phase, the intermolecular interaction is weak. When there's no intermolecular interaction, the gas is ideal gas. Let's first go over the units of pressure and temperature. In physics, pressure is defined as force divided by area. A large force, a small area give you a large pressure. In SI unit, force is in Newton, area is in meter squared. The combination of Newton per meter squared is also called Pascal. 1 Pascal equals 1 Newton per meter squared. Here shows a list of pressure units commonly used in engineering. The SI unit is Pascal. 1 Pascal equals 1 Newton per meter squared. Another commonly used unit is atmosphere. The pressure of 1 atmosphere can be measured by a tube filled with liquid mercury. The height gives you the pressure of the atmosphere. As we know, on Earth, the pressure of atmosphere varies, but the definition of 1 atmosphere equals 760 millimeter mercury height. Millimeter mercury height also called torr, so 1 atmosphere equals 760 torr. If we multiply density of mercury times this height times gravity, this will give you 101,325 Pascal. So 1 atmosphere equals 101,325 Pascal, or 1.01325 2.5 times 10 to the 5th power Pascal. A unit very close to atmosphere is bar. 1 bar equals exactly 10 to the 5th Pascal. One more unit that engineers like to use is pound per square inch, or PSI. The pressure is an indication of whether two gases are in mechanical equilibrium. For example, if two gases are separated by a movable wall, and if the movable wall moves to the right side, that indicates the left side has high pressure and the right side has low pressure. Conversely, if the movable wall moves to the left side, then the right side has high pressure and the left side has low pressure. When the movable wall doesn't move, that indicates the system is in mechanical equilibrium. The two sides have the same pressure. Here shows a simple question of calculating pressure. Suppose a person weighs 65 kilograms. Note the unit kilogram means its mass is 65 kilograms. Calculate the pressure he exerted on the ground when A, the boot's area is 250 centimeters squared, and B area is 2 centimeters squared. Without calculating, we know that smaller area means larger pressure, so B should exert a larger pressure. And pressure is calculated by force divided by area. 65 kilograms is not force. Force is calculated by mass times gravity. That gives you Newton. And so in A, we divide by area should be 200 centimeter. Now SI unit should be meter squared. So we use 250 centimeter squared. We times a conversion factor because we want to remove centimeter, so centimeter in the bottom and meter on the top. The relation is 1 meter is 100 centimeter. Okay, and because it's centimeter squared, we should square both. Okay, so that gives you 2.5 times 10 to the negative 2 meter squared. And the answer is 2.6 times 10 to the 4th power Newton per meter square, or Pascal. And in B, the area is smaller, and that gives you the larger pressure. A common temperature unit is Celsius. 0 Celsius is defined as the temperature of ice and water mixture. So when ice and water is in equilibrium, the temperature is 0 Celsius. The 100 degree is defined as the temperature of a boiling point. In engineering, Kelvin is more commonly used the temperature unit. Here's a comparison of Celsius and Kelvin. 1 degree in Celsius equals 1 degree in Kelvin. The difference is their 0 degrees. When water and ice are in equilibrium, the temperature is 0 Celsius. But the 0 degree in Kelvin is 273.15 degree below this degree. And therefore, if we have a certain degree in Celsius, the temperature in Kelvin, you should add 273.15 to get in Kelvin. For example, 25 degree in Celsius, we add 273.15, and that gives you 298.15 Kelvin. A gas phase is described by its volume, number of moles, pressure, and temperature. When 4 of these parameters are fixed, we say the gas is in a certain physical state. It turns out that these 4 parameters are not completely independent. When 3 of them are fixed, the 4th one cannot change. Mathematically, they are related by an equation called equation of state. Ideal gas law is one of these equation of states. It is important to remember a gas state is determined by 3 parameters or variables. The ideal gas law states that the product of pressure P and volume V equals number of moles N times R and T. T is temperature. In this equation, the unit of T always Kelvin K. The value of R depends on the units of pressure and volume used in this equation. If everything is in SI unit, and that is pressure in Pascal, volume is in cubic meter, then the value of R is 8.3145. Pascal times cubic meter is also joule, so 8.3145 joule per Kelvin per mole. When volume is in liter and the pressure atmosphere, then the value of R is 0.082057. When pressure is in bar and volume is in liter, then R value is 0.083145. If pressure is in torr, volume in liter, then the value is 62.364. The ideal gas law is a combination of several individual laws. This includes the Boyle's law, which says when temperature is constant, the product of pressure and volume is a constant. The Child's law, which says when the pressure is constant, volume and the temperature are proportional to each other. When volume is constant, the pressure is proportional to temperature, which is called Gay-Lussac's law. And the Avogadro's law, which says when both temperature and the pressure are constant, volume is proportional to number of moles. Here is an illustration of the Boyle's law. A gas in state P1, V1, and temperature T is sealed by a movable wall. When the weight increases twice, that means pressure increases twice. And you can imagine the gas will be compressed. Volume becomes half of initial volume, so half V1. All right, temperature is constant. So initially, the product of PV is P1, V1. At the final stage, the product of PV is P2, V2. But the P2 is twice P1, and the volume is half V1. So 2 cancel, that gives you again P1, V1. So the product of P times V is a constant that doesn't change when temperature is constant. We can see the Boyle's law comes from ideal gas law. When temperature is constant, number of moles is fixed, R is constant, so the right side is a constant, and therefore product PV is a constant. So initially P1, V1, in the end P2, V2, they must equal. Pressure, volume are inversely proportional when temperature is constant. When one is increased, pressure is increased, the other must decrease so that the product doesn't change. Here's a plot of pressure over volume when temperature is constant. Initially, here, let's say this is the initial volume, V1, and pressure, P1. And when pressure increases twice, the volume will be reduced half of it, V2. So here is the second. All right. So if you connect all these dots, you get this kind of curve, and this curve. So every point on this curve is at the same temperature, obeys Boyle's law, and it's called isotherm. Iso means same temperature. So isotherm represents the Boyle's law. So all these points represents the temperature T1. When temperature change, then all points move to another curve, T2. Here is a set of experimental data of 1 mole oxygen at 0 degree. When pressure is 0.25 atmosphere, volume is 89.6384. When pressure increased twice, volume reduced almost half. Increased pressure, reduced volume. The product PV is almost constant, 22.4, 22.3987. When we plot PV, P1V1, P2V2, P3V3, we get isotherm. Now, another way to plot this is pressure volume over pressure. When pressure increase, volume decrease, but the product of PV is a constant, 22.4. Note that in this set of experiments, pressure, the maximum value is 1 atmosphere. And under this condition, Boyle's law is obeyed. What if we increase pressure to very high? What happens to the volume? Here shows a plot of product PV over pressure with a larger pressure range from 0 to 500 atmosphere for different gases. So this is hydrogen and helium, argon, methane. At low pressure, when pressure approaches 0, if we enlarge it, we can see all gases merge into one curve. As we saw in the last slide, this is about 22.4. In other words, at a very low pressure, all gases obey Boyle's law. When pressure increases to 100 atmosphere or 200 atmosphere, and we can see that the product of PV for different gases deviate from each other. So at high pressure, gases do not obey Boyle's law. Boyle's law is a limiting law, only valid when pressure approaches 0. So why Boyle's law is valid only at low pressure when pressure approaches 0? What happens at low pressure? When pressure is low, molecules are far away from each other. The intermolecular interaction becomes weak. Remember, ideal gas is when there's no intermolecular interaction. So when pressure approaches 0, gas approach ideal gas. Boyle's law is a special case for ideal gas law. Here's the illustration of Child's law. An ideal gas in a state pressure P, volume V1, temperature T1 is sealed by a movable wall. And if the weight is kept constant, and that means the pressure is constant. And if we heat the gas, so temperature increase, we can imagine that when gas is heated, the volume will expand, so volume increase. When temperature increases twice, the volume increases twice. Volume, temperature are proportional to each other. We can also see Child's law come from ideal gas law. When pressure is constant, so P is constant, N constant, R constant, so volume, temperature are proportional to each other. Volume, temperature, proportional. And if we plot it, we should get a straight line. The slope increases when pressure decreases. Now for this equation, if we divide by temperature, okay, on both sides, so this divide by temperature, and we can see the constant equals volume over temperature. That means volume over temperature is a constant. So V1 over T1 equals V2 over T2. That's another way to say Child's law. Similar to Child's law, at constant volume, pressure is proportional to temperature. If we divide by temperature on both sides, the constant will become the ratio of P over T. So ratio P over T is a constant. P1 T1 equals P2 over T2. Avogadro's law states that for an ideal gas, when the temperature T, pressure P are constant, then the volume V and the number of moles N are proportional to each other. We can also see this come from ideal gas law, that when pressure and the temperature are constant, volume and the number of moles are proportional to each other. Just like other individual laws, Avogadro's law is only valid when pressure approaches zero. We have introduced the individual laws, including Boyle's law, Child's law, and Avogadro's law. When we combine all these individual laws, we get ideal gas law, which says PV equals nRT. If we divide by number of moles on both sides, then the right side becomes RT. The left side, V divided by N, is the molar volume, the volume per mole. So we have another way to write the ideal gas law, that is PVM equals RT. In this equation, there's no number of moles. An ideal gas or perfect gas is a gas that obeys Avogadro's law, Boyle's law, Child's law, and therefore the perfect gas law. Now don't forget that at the microscopic level, ideal gas is the gas with no intermolecular interaction, which can be achieved when the pressure approaches zero. Suppose we have two ideal gases, both obey ideal gas law. We can write P1V1 equals N1RT1, P2V2 equals N2RT2. In equation 1, if we divide by N1T1 on both sides, then the right side becomes gas constant R. Similarly, in equation 2, we divide by N2T2. And the right side also becomes gas constant R. Now gas constant R is the same value, and therefore we have a combined gas law which says P1V1 over N1T1 equals P2V2 equals over N2T2. Now for a same gas, N1 equals N2, and then we have the combined gas law P1V1 over T1 equals P2V2 over T2. This combined gas law is more convenient when we deal with a same gas that changes from state 1 to state 2. Here's a simple question. A 350 cubic centimeter sample of helium gas is collected at 22 Celsius and 99.3 kilopascal. What volume would this gas occupy at the standard temperature and the pressure? Now, standard temperature pressure refers to 1 atmosphere and 273 Kelvin. So this question is about the same gas but at different state. Okay, initially V1 is 350 cubic centimeter, T1 is 22 Celsius. Okay, you need to change to Kelvin, and P1 is 99.3 kilopascal. And then state 2, V2 is to be calculated, and the P2 is 1 atmosphere, and the T2 is 273 Kelvin. So because we have different state, it's more convenient to use the combined gas law. So here is state 1, and here is state 2, and we need to calculate V2. We use combined gas law. Okay, we can calculate V2. Note that in this equation, we don't have gas law, or gas constant, sorry. We don't have gas constant, but we still need to make sure the pressure, P1, P2, must in the same units. So in this case, is a kilopascal. Okay, so the 1 atmosphere should change to 101.3 kilopascal. And the volume are in the same unit. So V1 is in cubic centimeter, so V2 is calculated to be also in cubic centimeter. Now, if we don't have combined gas law, then we can use V1, P1, T1, so 3 variables. We can calculate the fourth one, that's number of moles in state 1. And because number of moles doesn't change, so we apply Vn to the state 2, so use ideal gas law twice. So first, use ideal gas law to calculate number of moles, and then use ideal gas law to calculate V2. Since ideal gas law can also be written as PVM equals RT, we can calculate molar volume by RT divided by P. Okay, for example, in the last slide, we showed that the standard state temperature pressure refers to 273.15 Kelvin and pressure 1 atmosphere. So plug in standard state temperature and pressure, we can calculate the molar volume to be 22.4 liter per mole. So all gases at the standard temperature pressure should occupy 22.4 liter. There's another closely related temperature pressure called the standard ambient temperature pressure. Ambient temperature means 25 Celsius, and that is 298.15 Kelvin, and the pressure instead of 1 atmosphere is 1 bar. So if we plug in those numbers, the molar volume becomes 24.8 liter. So far we have discussed the properties of pure ideal gas. What happens if we have a gas mixture? For example, in this container, we have a mixture of A and B molecules. Now, because both are ideal gas, so they have no difference, we can combine them together as total number of moles times RT equals total pressure times the volume of the container. And that's the ideal gas law. From this equation, we can calculate the total pressure equals total number of moles times RT over V. Now, total number of moles is the sum of the A number of moles and the B number of moles. Mathematically, we could distribute this product as Na times RT over V and B times RT over V. Now, first one, Na times RT over V, comes from ideal gas law that applied only to A. So that is actually the pressure that gas A would exert if it occupied the same container alone at the given temperature and volume. Okay, if you use ideal gas law to apply for A, as if there's no B in it, and that pressure is called the partial pressure of A. Similarly, the second term comes from the ideal gas law applied only to B as if there's no A in it, and that's the pressure that gas B would exert if it occupied the same container alone at the given temperature volume, and this is called the partial pressure of B. And therefore, in a mixture of AB, the total pressure is the sum of the partial pressure of A and B, and the partial pressure can be calculated using ideal gas law as if there's no other gas in it. The equation we just derived is also summarized in Dalton's law, which states that the pressure exerted by a mixture of gases is the sum of the partial pressures of the gases. And the partial pressure is the pressure that it would exert if it occupied the container alone at the same temperature, using ideal gas law. Since ideal gas law is used, Dalton's law is a limiting law that only true when pressure approaches zero. Here's a sample question. A container of volume 10 liter holds 1 mole of nitrogen, 3 moles hydrogen at 298 Kelvin. What is the total pressure if each component behaves as ideal gas? According to Dalton's law, we can calculate partial pressure and add together to total pressure. So the partial pressure can be calculated as if there's only one gas in it. So partial pressure of A using number of moles A times RT over V, and that gives you 2.45 atmosphere partial pressure A. Similarly, you calculate partial pressure of B, you get 7.34, and then you add together. That's the total pressure. Another way to do it is because both are ideal gas, we can combine them together. So the total pressure equals total number of moles times RT over V. Okay, using one ideal gas law, we can calculate, give you the same answer, 9.79. When we have a mixture of ideal gases, we can calculate the partial pressure of A using number of moles A, and the total pressure using total number of moles. And the equation 1 divided by equation 2. So the left side is the partial pressure, A divided by total pressure, and the right side, the RT over V cancel each other. So you have a number of moles A divided by total number of moles. And the right side is also called mole fraction. Okay, it tells you the percent of A in the system. So this equation leads to an important equation, and that is the partial pressure equals total pressure times the mole fraction. And this equation tells us that the contribution of A to the total pressure depends on the mole fraction. Okay, the higher the concentration of A in the system, the more the A contribute to the total pressure. When XA equals 1, then it is a pure A. So this equation says the partial pressure of A equals total pressure. We have derived these three equations for mixtures. The partial pressure is calculated by ideal gas law as if there's no other gas in it. Partial pressure is total pressure times mole fraction, and the total pressure is the sum of partial pressures. The first equation is only valid for ideal gas because it's ideal gas law. The second and the third equations, although derived from ideal gas law, they apply to non-ideal gas because the contribution of each gas to total pressure must be proportional to the mole fraction or percent of the molecules in the system, and the total pressure must be the sum of the partial pressures. Sample question. The mass percentage composition of dry air at sea level is nitrogen 75.5, oxygen 23.2, argon 1.3. What is the partial pressure of each component when the total pressure is 1 atmosphere? First, this question doesn't say this is ideal gases, and therefore we cannot use ideal gas law. Instead, we use partial pressure equals total pressure times mole fraction. Total pressure is given 1 atmosphere, and we need to know the mole fraction of each component. The question tells us the mass percentage. How do we convert mass percentage to mole fraction? One common strategy for this conversion is we assume the mixture has 100 gram mass. So the total mass is given. Then the mass of each component is just the percentage value. So 75.5 gram for nitrogen, 23.2 gram for oxygen, 1.3 grams for argon. Okay, using these masses, we can calculate the number of moles. So for example, nitrogen, you use 75.5 divided by molar mass. Note that nitrogen is a diatomic molecule. So in periodic table, you'll find it's about 14 gram per mole of nitrogen, you times 2. Okay, don't forget times 2. Similarly, oxygen use 23.2 divided by 16 times 2. All right, don't forget times 2. They are diatomic molecule. On the other hand, argon is monatomic, so 1.3 divided by 39.95, and that gives you 0.033 moles. Okay, with this number of moles, we calculate the mole fraction. So, for example, nitrogen mole fraction is 2.69, which is the number of moles of nitrogen, divided by total number of moles. That gives you 0.78. And then plug in this equation. So total pressure, in this case, is just 1 atmosphere. So the partial pressure of nitrogen is just 0.78.